Okay, first thing I want to do is just, prep you on the schedule again. So this past Tuesday, we were doing moment calculations in 2D, and it was using the right-hand rule. And we're gonna, wait, hang on, I'm just moving your photos. And I'm gonna post now the solutions to the homework. I'm gonna publish it rather, not post it. I'm going to publish the solutions so that you could check your solutions out with mine. And it's due on tomorrow. Okay. Today's lecture is on moments in 2D and 3D space using vectors. Okay. And you'll notice there's an overview here, which says, by the end of this module, you'll know how to calculate a moment about a point, moment about a point. Oh, there's a little mistake there. Edit. A moment about a point vectorially. So I'm differentiating between solving for moments using a right-hand rule. And remember, the right-hand rule is where you're taking the magnitude of the force, the magnitude of the perpendicular distance, and then using your right hand to determine whether it's positive or negative. And the other way of solving moments is vectorially, where you're finding out what the R vector is, finding out what the F vector is, and crossing them. Okay? The moment that and you also know from both physics and math, definitely from math, that when you do the cross product, the moment vector is the vector perpendicular to both the R vector and the F vector. Let me say that again. When you use the cross product, when you say R cross F, when you use the cross product, let me also say that the cross product gives you a moment vector, which is a vector perpendicular, maybe it gives you a moment, which is the vector perpendicular to both the R and the F vector. You already know that, right? Okay. And then notice how I set up the vectors. The way I set up the cross product. Everybody put yourself on mute, please. Oh, and do I have to pin myself? David?
Yes.
Okay, hang on a second. So just everybody be quiet for a minute. So when I'm trying to find a moment about a point, notice I put the subscript of the point I'm trying to find the moment about. So the moment about A is equal to, then I'm jumping to the F. The force vector is from the tail to the head, which we're comfortable with already. So if I'm trying to find the moment about point A, due to the force BC, my R vector goes from the point I'm finding the moment about to the tail of the force. Okay, I'm going to say it one more time. When I'm doing the cross product, I'm trying to find the moment about a point. And the subscript of the moment is the point I'm trying to find the moment about. The subscripts of the force represent the tail to the head. So this force goes from B to C. And then my R vector goes from the point I'm finding the moment about to the tail of the force. And I'm going to say this a bunch of times today. So if you look at this, you could see, oh, here's an A, here's an A, here's the B, here's the B. So there's a repeat of variables, point A and point A. And then depending on where the tail is, point B, point B. Okay, I'm going to save this now, and now we're going to go through and do some problems. I have to move my pictures again. And I'm going back to modules.
Joanna, I have a quick question.
Yeah, hang on a moment, okay?
Okay.
Let me go, when I stop sharing, I'll do the pin thing. So Tuesday's lecture, we did a few 2D finding moments about a point in 2D space using right-hand rule. And today we're going to solve for moments in 2 and 3D space vectorially. But we're going to start out the class with doing a 2D problem, and we're going to do it doing the right-hand rule first, because that one's a little, right-hand rule is a little tougher. So we're going to do a 2D problem using right-hand rule, and then do the same problem using vectors. And then we're going to move into a 3D problem using vectors only. Okay, so I'm going to stop sharing my screen for a moment, and I'm going to make sure that I pin Okay, David, remind me where the pinning is.
I think that's if you mouse over yourself and then you've got
Oh,
the
over
three dots.
myself, right. I got to
Yeah.
go over myself.
It's wherever the work you're showing is going to be. So I don't know if you set up the two
Okay.
cameras
Yeah.
or whatever, but
Okay. All right. So, great. Okay. Maria, question.
Yeah, I was just wondering, it's always R cross F, right? Not F
Yes.
cross R.
Correct. R cross F.
Okay, so the order.
You'll get the opposite. You'll get the opposite sign. It'll make it look like the moment's spinning in the other way.
Oh,
Okay, so it's got to be R cross F.
Thanks.
Okay. Okay, so I'm going to now use the document camera. Great. Okay, can everybody see this problem?
it's good.
Could you read it? Okay, so it says there are forces F1 and F2, and look at the picture, and sure enough, there's F1 and F2, and they tell us the value of each of the forces there. And they also show us the direction. You know, when I'm doing grading, I'm still looking at your free body diagrams because those are so important in statics. And sometimes you guys are still leaving out the direction of the force. You do show, everyone's showing arrow. Everybody's writing the variable or the numerical value of the force, but many times you're leaving out the direction, which either can be written in an angle form or in distances. Particularly with the 3D problems, don't get sloppy. Those 3D problems just take a long time to draw, and you got to draw them clearer.
So, we're for the moment ones, we're still supposed to be doing free body diagrams because it wasn't listed in the steps.
No, you don't have
good.
to. I'm just mentioning that this is a nice free body diagram, and when we do statics problems, we need a free body diagram. But for the moments, we don't. So if we go back to the beginning of the class, okay, number one, the first thing we did, hey, did you know that in the United States, whenever we say one, we do this, right? 1, 2, 3, right? And yes, Jordan, what Jordan's doing, in Europe, they do 1, 2, 3. So if you put out your 2 fingers, when we think it's 2, they think it's 3 because you forgot to put out your thumb. Anyway, just interesting. Okay, has nothing to do with statics. Okay, number one, we first did components in this course, right? We learned how to do the 3-step process and all the checks. The next thing we did was solving for resultants. We statics teachers and statics authors of books want to make sure that you're comfortable doing resultants. And yes, when we solve for resultants, it's not statics because we're getting a value for resultant, right? So when we get a value for resultant, we're really looking at some dynamics going on. Third, we learned how to start doing statics of particles problems. We did setup, and then we did the solution, right? Okay, so now we're going into moments. We're solving for a moment. When we solve for a moment, is this thing moving? Come on, give me.
No, it's not moving.
Okay, if when I solve for a moment, like on Tuesday, when we solved for moments, we did get values of moments, right? And when we got values of moments, it was actually moving, right? Because we're getting a moment, which means what kind of motion? What kind of motion is something happening when there's a moment?
Rotational motion?
Rotational motion. So it's rotating. Okay? So when we had all our forces, we were looking at translational motion. When we had all our forces acting at a certain point and we were looking at a particle, we were only having translational motion. Now we're calculating moments about points. In this case, it's asking you to find the moment about point A. Here's point A right here, right? Granted, this is a fixed support, and we'll learn about supports in a few weeks. Certainly, these forces are trying to cause us to move, but in the end, it's going to be prevented from moving because of this connection, this fixed support. But right now, just like we practiced how to find resultants, we're practicing finding moments. Because when a force is applied to a certain point, this other point is being caused to spin. Okay? All right. So first thing we're going to do is we're going to solve for the moment about point A using right-hand rule first. And if you remember from Tuesday or you watched my video again, the first thing to do is see, are the perpendicular distances given? So let's take a look. We have F1 and we have F2. Do we know the perpendicular distance? I'm going to just start in the middle. So I'm going to start with Jordan. For F1 and F2, are we given the perpendicular distances to point A? From F1 to A. So again, what I always do in these problems is I look at the line of action of the force, right? Because I want to become more comfortable finding the perpendicular distance. Where is the perpendicular distance, Jordan?
I think it's given.
Well, the perpendicular distance from the line of action of the force to point A is this right here.
Oh, that's not given.
That's the perpendicular distance. And I know maybe this is hard to see, but you have to figure out how you're going to see it. For me, I take a marker or whatever, and I put the whole line of action of the force here. How about for F2? Here's F2. Jordan, is the perpendicular distance between A and point and F2 given?
No, it's not.
No. So the first thing you're doing is you're checking out to see if you have the perpendicular distance, because remember that a moment, in order to calculate the moment, it's the absolute value of force times the absolute value of the perpendicular distance, and then you use the right-hand rule to find whether it's positive or negative, right? This is the steps for finding moments by right-hand rule. So if the perpendicular distance is given, then we could go ahead and find the moment. But if the perpendicular distance is not given, then instead what you're going to do is you're going to break the force into components. Okay? So we're going to break the force into components. F1, find the component. F2, find the component. And I believe I already solved for them. I didn't. So let's think about this. You guys, we're going to Cody. Is Cody here? Okay, Laura? Okay, let's think about this. We could solve the moment about point A due to F1 when there are two forces present. We have to find the moment about point A due to F1, and we have to find the moment about point A due to F2. Because both forces are coming off the same point, do you have an idea of what we could do to simplify these two forces so we only have to find the moment about one force? It's a tricky question. But right now, there are two forces at this point. Could I make it so there's only one force at this point? And what would I do?
Yeah, it seems like you could. Oh,
Jason, wait,
Nope.
it's Laura.
right.
Sorry, Jason.
I know you're trying
I
to
know-
save her, but she doesn't want to be saved.
No, just forgot.
Let's see.
What have we done in the past when we have more than two forces at a point?
Oh, we broke them up into components,
And
and
then,
then we added each component with each
right,
other.
so in the end, what did we do? We found the, what's the word for the sum of those forces?
What's the word for the sum of the?
Yeah, let me go on. Liam, when you sum up forces, what is it called?
The resultant?
The resultant, right? Does that make sense? So everybody take a look at the problem again. I'm always picking, every problem I do in class, I'm picking something that's a little bit different from the previous problem. The previous problems, we had two forces and they were both being applied at different places. So we had to find the moment about each one. Or we broke the force up into components. In this case, we have two forces coming off the same point. So let's find the resultant of this force, and then we only have to find the moment due to the resultant. And I'm going to skip it all because we know how to do the math already. The resultant turns out to be (5.65i) plus 1.41j. And it's kilonewtons. And I want to make, but ordinarily, you need to find the components of each force, right? You need to do your checks, and then you add up the resultants. You add up to create the resultant. Did you guys notice that I have 2 decimal places here instead of 1?
Yeah, I was going to ask about that.
Yeah. Remember, our rule up till now was to use 1 decimal place more than the given problem. When we start working with small numbers and we're using moments, moments is the next step, right? All our problems up till now stopped with a force, and we represented it as 1 decimal place. But I'm concerned that if I only use 1 decimal place and then I'm multiplying it by the distances and I round and then I get the moments, I'm feeling like I'm going to get more rounding errors. Okay? So I'm going to start, leaving maybe 2 decimal places instead. You'll notice I might fluctuate between 1 and 2 decimal places because depending how large the number is, like this number is so small, these decimal places are really going to govern. Where if the resultant was 105, I probably would only put 0.7. But because it's small, I'm starting to put another couple of decimal places. So when we start statics, I'm really particular about things because I want you to get in line and following the rules so you're comfortable with what the rules are. And then at times we're going to start to deviate because now you could skip a step because I'm okay with you skipping steps now. Okay, so here's the resultant force. But remember, you would have to find the components and you do the checks and then you find the resultant. Okay, so now I know that resultant X is here and resultant Y is here. And how come I'm drawing them both? Where am I? Luis, why am I drawing both the resultants positive?
Because the results are positive, so you
Right, because I calculated positive values, so I drew them positive. So now I'm going to do the right-hand rule. I'm trying to find the moment about point A. And remember, we still have two forces. So it's the result, the absolute value of the first one, 5.65. And Mackenzie? So the absolute value, I'm doing Rx first, the X component, 5.65. What is the perpendicular distance between the force here and point A? So can you see that? I'll do it in a different color.
Yeah, is it 500 millimeters?
Okay, let's check. Here's Fx, and here is point A. So it's
Oh.
not 0.0. If it was 0.0, yes, 500 is correct. But we're doing about point A. So somehow mark on your picture where the point is you're trying to find the moment about so you don't make that kind of mistake.
Okay.
So what is the distance then?
500 minus 125.
Right, so that's 375, right?
Yeah.
Okay, absolute value of the force, absolute value of the direction, the perpendicular distance. Right, here's my force, here's my perpendicular distance. I put my fingers in the direction of force, palm towards A, and I get?
Negative.
Negative. Okay, Marcine, you're next. The value of the force in the Y is 1.41. We're looking at now this force, Y, and here's point A. What is the perpendicular distance? This might be hard for you to read. I don't know if you could see this.
Is it 300 minus the 35?
Yes, I think that's halfway. Let me just look on my better picture.
Yeah.
Yeah, boy, even all my photocopies are crappy. Let's just say it. Let's just say that it is this from here. You could see that, right?
Yeah.
Is 35. So it would be 300 minus 35. So that's 265, right?
Right.
Okay. Positive, negative. Finger goes in the direction of the force. Palm goes towards the point. Positive or negative, Marcine?
Positive.
Positive. Okay, and I think I need my calculator.
Can I have a question?
Yes.
Why did we reverse the order of R and F? Like, what's for the right-hand roll? Why is that reverse?
That's more of a, I guess what we can do here if we want, I mean, the vectors are R cross F period. Okay, so we always do R first, then F. Why in right-hand rule, the question really is, why in right-hand rule do we do the force first? I don't know, it's just been the accepted practice. The accepted practice is to do the force times the perpendicular distance. But if you want, you could do the perpendicular distance first and then the force. It doesn't matter because they're both absolute values. Doesn't matter.
And it's just multiplication, not
And
a
it's just
cross product.
multiplication. But it's the accepted, if you look in the text, that's just the accepted. Okay, 5.65. Did somebody get an answer yet? Come on, you guys, you're supposed to be faster than me on this.
I think it's negative 1745.1.
I agree.
Great. And what units? Kilonewton millimeter.
Is that an acceptable unit, or should we move it to meters?
It's fine. You could move it to meters, though. I mean, we just have to be careful because when you move it to meters, God, we could drop off so many significant digits, you know?
Yeah, that threw me off a couple times on the homework because the units would all be different. Like inches to feet came up once or twice.
Yeah, because they're trying, you know, this is the country we're living in.
That's why I'm asking. Is it acceptable to have kilonewton millimeter, or in the homework it was like inch pounds?
Inch pounds. You use whatever is given.
Okay.
You can convert the middle millimeters to meters, but just be careful with significant digits. So I probably would just use the units given.
Yeah, I don't want to. I'd rather leave it like that.
Yeah, just leave it the way it's given.
Okay, great.
Okay.
I have another question.
Wait. Hang on. Let me finish. Damn, what was I going to say? Oh, tell me what, where are we? Maria, What is this spinning about?
The point A.
It's point A, correct. It's the moment about point A. But where is the spin? Is it rotating about the X, Y, or Z axis?
Oh, about the Z axis.
How come?
Because that's in the XY plane. The picture's in the XY plane, so the rotation has to be around the Z axis.
Correct. All the forces and the distances are in the XY plane, so the spin is in the Z. And we got a negative spin, so which way is it spinning?
Clockwise.
Clockwise. So I'm going to put the K here, which is a little confusing because we have a kilonewton here. You know, so maybe it's better to put the K inside the parenthesis. But again, in a 2D problem, you do not need to write the K. We all know in a 2D problem, the spin is about the Z axis. But when we get to a 3D problem, we're going to have to write I, J, and K. So I want to ask you, remember, this is way back at the beginning of the semester. I am drawing the arrow like that. So where are we? Matthew. Is Matthew here? Matthew. Did I just draw the spin around the point A correctly?
No,
How come?
because the spin is negative.
Great. Is this right?
Yes.
There, it's right. That is the way the spin is going. Remember, take a look at this. Can you see here? And let's say this is the y-axis. So we're on Myra. This is the y-axis. How is it spinning around the y-axis? Positive or negative?
Positive.
Great. Excellent. You put your thumb. You see my fingers are curling. My fingers are curling around the way that is here. And my thumb is going in the y, positive y. This is a positive spin about the y. Notice here, this is really important because the textbook will confuse you. Well, let me say first, notice here, see how I put a little space here to show that the spin is going behind the axis? I did not do that here. I crossed the bar in both cases because I'm trying to show that it's going like this. It's not going around the bar. It's a spin in the Z. Does everybody see the difference between these two drawings? Okay, Jason, you said you had a question.
Yeah, now I have two. Would you ever actually have a spin around the Y like that?
Yes.
Because that implies three-dimensionality, but you know, if your convention is that you always start with X, Y, and then add Z, that if you had Y, you wouldn't have
Okay, yeah, let me answer that question.
yeah, thank you.
And it's getting us a little bit further, but I want you guys to think about this. Everybody with me? The resultant force of X is intersecting, the line of action is intersecting the y-axis. It can't create a moment about the y. And the resultant y is intersecting the x-axis. It cannot create a moment. There's no lever arm. So a force in the x and y can only create this moment. When we get to 3D, which we are in a little bit, and let's wait until we get to a 3D problem, and then we can talk more about where the moments are being created. Okay, Jason, what's your second question?
The second question is, where is this magnitude bars coming from? Because it seems like it would be equally as effective to say, what is the absolute value of these scalars?
Okay, so this is what I remember when I was a student. The double bar represented a magnitude of something. Now, I don't know if it's a single bar now or something else, but this is my representation. And I always write it because I don't want to put a negative X, a negative distance. I never want to put a negative magnitude. These are supposed to be both positive numbers because they're absolute values. And when we're finding the moments due to the right-hand rule, we are we are only finding the direction based on my right hand. I am multiplying the magnitude of the force and the distance.
I suppose my point is that the
Let's
magnitude.
just keep going. Okay, I'm going to erase my line here so I have more room. Okay, now I'm going to solve this vectorially, and you guys are going to fly through this. So we know the moment is about what, Miles, what point are we trying to find the moment about? Okay, Peter, you here?
Yes, now we're looking.
What are we finding the moment about?
Now we're looking for the moment about point O.
No, we're still doing point A.
Oh, okay.
We're doing the moment about point A in both cases because we want to make sure we get the right answer. The same answer. It's a check. That's what's great about statics. There's always checks. It's great. So when we design a bridge, we could check it so it doesn't fall. Okay, we're trying to find the moment about M, and it's R cross F, and I always do F first. So where is F coming from? Well, we don't have a point up here, do we? So we have an A, we have an O. It's an R. Let's just call this point B, okay? Everybody good with that? I'm going to call this point B. So my force is B. I'm not drawing where it's going to because it's a resultant now and it's up here somewhere and I don't want to calculate it and I'll draw it. So my force is at point B. So Peter, I'm going to stay with you. The overview that I showed you originally from the module, do you remember what two letters go here for the subscripts of R?
No, I don't.
Okay. Okay.
Which I can look at them.
Well, it's okay. Let's just, Tim?
It goes from the point to the tail, or to where the force is going, so A to B.
Right. So it goes from the point I'm finding the moment about to the tail of the force. So whenever I do it vectorially, I wrote M equals R cross F. I put M subscripts in, the point I'm finding a moment about. F, I put the subscript of B. And then R, I put the subscript of the point I'm finding the moment about. So it's interesting because look at this. This is this, right? And this is this. And if the force went to another, this was the head of the force, it would still be like this. So this is a good way of remembering it. So RAB. Tony, you here, Tony?
Yeah.
Okay, great. So you see where R is, right? And you see where B is. What is the X value, the direction from A to B in X?
I mean, I can't really see the picture.
Yeah. And the picture has so many lines on it, might be hard to tell. But we're going from A to B.
Uh-huh. Well, so you wanted to know the X distance, right?
Yeah.
300?
Right, it's 300, but it's 300 to the middle of the bar. And remember, this is 35 and A is on the edge. So you got to subtract these two. So it's 265. 265. And is it going from A to B? Is it in the positive X direction?
Yeah.
Great. Okay, now on Victoria, going from A to B, what are we going in the X?
In the X?
Yeah, no, I'm sorry, in the Y. We already did the X, sorry.
In the Y, isn't it 375?
Yep, and is it positive or negative?
Positive?
Yep, be confident. Okay, and we already know what the force is up here. So I'm gonna move it up. Moment is equal to R cross F. We have our R vector, we already have our F vector. So moment about A is, and did you guys do this in math? Or I don't think you did it in physics. Maybe you did, I don't know. The force is 5.65, 1.410. You guys, give me a thumbs up or something. Did you guys do this, these matrix thing?
Yes,
Okay.
we did do that in math.
Okay, and so there's a number of ways of doing it. I'm just really refreshing your memory because you probably are experts on doing this. But just for a moment, could you just stop and watch me for a minute? The way I tend to do it, but it is kind of a long way, and some of you might not like to do it that way, but I do it because then I feel like I'm going to make less error, but it's longer and you don't have to do it this way. So you do it whatever way you want, but I'm going to show you. One way is you go this, 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 add them all up. So this, minus this, this. And those of you who took surveying, remember double area method? Marcine, Maria, Matthew, who else was in surveying? It's like the double area method, but you don't divide by 2. Okay, so this is one way to do it. Another way, which probably more of you do, is you take a look at, or you take a look at the I, and you do the determinant here, and then you subtract the J, determinant this and this and this and this, and then you take the K, and you do this and this. Is everybody following what I'm saying? So you take the orange and this determinant, the determinant of it, you take the J, but you have to remember that it gets a negative, and you do this and this, or you do the K and you do this and this. So basically you are not using the column that the guy is in, all right? In this case, you notice there's zeros, right? So if I did the I would get a 0. If I did the J, I'd get a 0. The only thing is the K, which is correct because it's the force is in the 2D plane, so the moment has to be in the K. So it turns out to be 265 times 1.41 minus 375 times 5.65, and plus minus, and it's all in K, and it is kilonewton millimeter, and the answer turns out to be negative 171,745.1 K kilonewtons millimeter. Let me just move it up in case you can't see it. If I took a vote right now, my prediction from teaching statics so much is that you prefer the vector method to the right-hand rule. Is that true?
That is true. That is true.
Yeah.
So show me V if you like vectors. Okay. By the end of the course, you're not going to like V. Ghostbusters. You're going to like the right-hand rule, and you want to know the right-hand rule. Think about this. You work for Specialized Bikes. You're designing a bike. You're trying to find the moment of 1 bar due to the weight of the person on the bar. You are not going to take out a piece of paper and do vectors. You are going to look at it. You're going to know which way the load is, and you're going to use your right-hand rule, find the perpendicular distance of the right-hand rule, because that is the correct way of looking at it. Plugging and chugging numbers is not engineering. But it's a great way to check things. So we're learning both ways. Okay, does anybody have a question on either method? Next step is we're gonna do a 3D problem vectorially. Basically, think about it. You could go through and do vectorially without really even thinking about physically what's going on. When we did the right-hand rule, we really had to figure out where things are, what kind of moments it's causing, what's the perpendicular distances. It's more of a physical thing. Okay, Maria.
Did we get the same answer for both of them?
We should,
Okay.
because look, take a look. It really,
Yeah.
they both really are the same method, right? In both cases, we're multiplying 265 times 1.41 and it's a positive. And we're multiplying 3.75 times 5.65 and it's a negative. It's really the same. You know, doing it like this is really doing it. I just call them different, the process, because it is a different process. Vectorially, you're finding the vectors and using the cross product. Right-hand rule, you're finding the forces looking at the perpendicular distance and using your right hand.
Okay, I just did it wrong. Thanks. I
Oh,
actually
okay.
like the right hand rule better.
Say it again?
I like the right hand rule better exactly because of what you were saying about like it just makes more sense to me versus like just the vectors.
Okay, so far I have one recruit, Maria. But as you go up, Marcine, you're a recruit too. Okay, so now show me the V up for vector and the V down for not vector. Oh, David's down too. Maria's down, okay.
Yeah, I think the amount of fiddly calculation you have to do to hand draw a matrix manipulation like that is too much.
Yeah, okay. Okay, so now we're gonna do a 3D problem.
Joanne, quick question.
Yeah.
Can't you just like plug and chug on your calculator for the vector and the cross product?
Oh yeah, I'm sorry, I never stopped. I got on my soapbox, right? That's what it's
That's
called.
okay.
I got on my soapbox with which way I like better.
Right.
Okay, so in addition to doing, so one way is to do this, the slashes. Oops, wait, hang on a second. One way is to do the slashes. The other way is to go I times this, the determinant, J minus J, the determinant, and K minus the determinant. The other thing is you plug it in your calculator, which you're doing, or maybe you already handed it in, that whole calculator thing. And the calculator doesn't want, I believe, and I could be wrong, and you figure it out for yourself. I believe that a calculator will not find a determinant with an I, J, and K in it. So what you have to do is put in 3 different determinants on your calculator and then multiply them by I, J, and K. But you guys figure it out.
It's
David?
easier than that. It's easier than that.
You want to
can just-
explain it?
Yeah, you can just do a matrix that's 2 by 1. That's 265 and 375. That's matrix R. And then you can do
Okay.
another matrix that's 2 by 1. That's 5.65 and 1.41. That's matrix F. And then
You mean 2 by 2s, don't you mean?
no, I mean 2 by 1.
Say it again?
The first R, right? Matrix R is just the 2 components of it. It's just
Oh, right.
265
Okay.
and 375.
Right.
Matrix F is just the 2 components of it, 565.
Oh, and then just tell it
141.
to cross.
And then you say R cross F on a calculator and it does it right.
Gotcha. Okay, everybody, did you hear that? That was important. In your calculator, you put in the R vector, you put in the F vector. They're both 2 by 1s, which means it's a 2. Remember, matrices, 2 by 1 means this is always rows and columns. So you put in the R vector of AB. Put yourself on mute.
I might have meant 1 by 2. I'm not sure it matters. But
Okay, so we're not sure whether it's a 2 by 1. You guys, you have to put yourself on mute. Somebody's printing something.
Joanne,
Daniel?
you can mute the class.
Oh, okay. All right. So I don't know if it's a 2 by 1 or a 1 by 2, but the point is what David's saying is you could put in the R vector into your calculator, put the F vector into your calculator, and just tell it to do the cross product. That's the best. That's the quickest.
Does that work for 3-dimensional vectors?
Yeah. Yeah, if the calculator can do a cross product, it can.
yeah, I think that'll be significantly easier if we're starting to
Yes.
do these with 3 components than just typing in multiple matrices will be faster.
I agree. Okay, so now we're looking at a 3-dimensional problem, and these problems are written, these problems are on the module. So notice we have a box here. I'm going to kind of fill in the box a little bit just so that you could see it in 3D. Oh, another thing is you guys still have to practice 3D. Some of you still are not seeing things in 3D. Okay, the question here is to find, I'm going to tell you what the force value is. I just have to look it up. So F goes from A to B, and the value is negative 360I. Nope, that can't be. I must be looking at the wrong problem. Why? Why do I know that's wrong?
It goes in positive X.
That's right. Good job, right? A to B. Let's just look at this. Going from, where am I? I'm up at the top. Adam here? Okay, Amani.
Yep.
Going from A to B, is it going in the positive or negative X?
In the positive X
Right.
direction.
In a three-dimensional problem, always look at where these axes are, because you can put them wherever we want, right? Well, in this case, the XY plane is on the floor, on the ground, it's horizontal, and Z represents the elevation. Many times X is here and Y is here, right? XY is the vertical plane and Z is coming out at you. So going from A to B, it's in the positive X. Mani, how about Y?
And the positive Y too.
Positive Y, correct, because look at Y, this is the distance here.
And
then what
negative Z.
about the Z? Negative Z. So
Negative
if I wanted, and again, I like my parallel rule that I use from graphics, but again, you know, you don't have to have this. You just need to make sure that you're drawing things parallel. So I'm just turning this for a minute just to make it easier for myself. Here is the Y axis. So here's the force going in the Y. Here is the
That's
X
Z.
axis.
That's Z on this drawing.
Oh,
right?
thank you. I'm just going to go over it. Okay, you guys. Z. Thank you, David. Okay.
Yeah.
X axis, parallel. Here's my FX. FY. Here's FY. It's right along here. And the reason why I took a long time to do this is I want to show you that, you know, you're looking at lines being parallel. X is parallel to X, Y is parallel to Y, Z is parallel to Z. Make sure you draw it that way. So you can see that FX is going in the, is positive, FY is positive, and FZ is negative, okay? And I want to call F going from A to B, so I really should have put AB next to all these guys. And I'm just going to wipe this whole thing out just so I can move and write somewhere else.
Is there a convention for that notation? Because I've run into that a couple times. Is it proper to say FABX, or do you want it to be FXAB?
I think it's FAB because it's the force AB in the X.
Got it.
Have you seen it differently?
No, that's what I'm
But
asking.
it doesn't really matter, you know, I know what you're talking about, but I would call it FAB in the X. Okay. So FAB, oops, FAB. I just want to make sure I'm looking at the right problems. Just hang on a second. Yeah, so it's 400I plus 500J minus 600K. And the units, what are the units? Angel?
Is going to be in newtons.
Right. Right. And I didn't tell you what the original value was, but can you find what the original value of force was? How do you find, Angel, how do you find the original value of the force?
you square root each component squared.
Yeah, so why don't you do that so we can make sure we put the right number. I'd like to have the magnitude of it too.
Let me see.
Come on, you guys, the calculator experts. I shouldn't be able to do this faster than you. 734.6.
Yep, I got the same.
Okay, so we have the force. So we want to find, the question is finding the moment about point C. So I want to find the moment about C. I have R cross F, or I already know F goes from A to B. So Bon, where does R go from and to?
From point A to C.
Okay, the first point,
Oh,
again,
C.
C to A. And remember, the reason I remember this is I write this first. I just go from left to right, okay? We already have FAB, so let's do RCA. Hey, do any of you remember RCA? That they made radios and not radio, anyway. The RCA building is not called the RCA building anymore in New York. Okay, RCA, we are on Colin. Colin, are you here? Okay, Daniel C, you're here. Daniel.
Yeah.
So R, going from C to A.
Yeah.
Again, this is what we need practice in, right? We're going from C to A. This is my RCA vector.
Yeah.
And how much am I going in my X? I look at the X axis.
Isn't 100 millimeters?
Yep, it's 100. And is it going in the positive or in the negative?
If we're going from point C, then it'll be negative. But are we
Right,
going from the center? Okay.
Going from C to A, negative. Okay, how about Daniel H? What about Y? Here's my Y axis. Going from C to A, what's the distance I'm going? Okay, Daniel I. From C to A.
Would that be 250 millimeters?
Yep. Positive or negative?
Positive.
Positive. And David L. Going from C to A and the Z, what am I going?
I think it's positive 180. It's the 120 and 60 together.
Correct.
Okay.
The 120 goes from this dot to this dot, and the 60 goes from this dot to this dot.
All right.
180K. And David, what's the units?
Those are millimeters.
Millimeters. Okay. So your R vector, remember it's a distance. A lot of people mess this up. R is the distance. It has a distance unit. Okay. So according to what David said, I don't even have to draw the matrix, but I'm going to draw it anyway. MC is equal to IJK. The R, remember the R goes here and the F goes here. The R goes in the second row. So R is negative 100, 250, 180. And F is in the last row. But if you're just going to do it by the calculator, you just write calculator. Just write calculator R cross F and tell me what the moment turns out to be. So whoever knows how to, David, you know how to use that on the calculator?
I'm working on it. This
All
is
right,
an
thanks.
interesting case to see if it's actually faster.
Okay.
Joanne, can you move the paper up a little bit?
Yes.
Thank you.
Good. And I'm going to write down the answer I have. I have negative 180I plus 36J minus 150K. And the units are Newton millimeter. Okay, everybody with me?
So the calculator version will work, but it gets you thousands, right? So because it was in what?
Oh, wait, I'm sorry. I converted it, didn't I? Sorry,
Yeah, so
I'm looking at my notes. So this is meters. You
yeah, so
guys, before we go on, hang on. You guys, I plugged in millimeters, but then I represented the answer as meters. Is everybody comfortable with that? I just moved everything over. Everybody's okay?
Yeah.
Okay, but you got the same answer. Okay, you guys, take a
Yeah.
look at this now. Here's the visual thing, the meaning of this. I am calculating, where are we? We are on David LR.
Yeah.
David, we are calculating the moment about what point?
C.
Point C. So here's my point C, right? And I am calculating a moment about the X, Y, and Z axis through C. Does everybody agree? I am finding this is the X-axis through C. This is the Y-axis through C. This is the Z-axis through C. I calculated the moment about point C around the X, Y, and Z axis through C. Is everybody comfortable with that? I did not find the moment about point O. I am finding the moment about point C, and I'm finding the X, Y, and Z component of the moment about C. Dave, I'm going to start calling you Dave because
I do it intentionally because there's a couple Davids.
Okay.
That's a new concept, right? The
Right.
last one we got one number for a moment, right? And now we have a spin around all three. So
Three
actually,
axes.
there's a spin around X, there's a spin around Y, and there's a spin around Z. That's the three components we got.
That's correct.
Okay.
Well, we
This
were
is the
always
fir-
getting
this-
a component.
Right, but we were
Oh, and the other
only
ones, we had
but
some
we
Z
were
ones.
only getting the Z. So in this, all the 2D problems, we only got a moment about the Z axis. And that's why I kept putting K.
Ah, you
Because
know
the-
what? You know what
Hey,
actually
wait,
helps?
you guys, let me finish my sentence and then you could cut it. So in this problem, the forces and the distances were all in the XY plane. So the only moment I got was a spin in the Z. Now our forces here, our force, actually there's only one force. This force has an X, Y, and Z component. It is creating a spin around point C in three different components. And this is the first time you are ever experiencing this, the first time. So it's going to take a while to get it, okay? But realize in the other problem, I think you all got this, in the other problem, X and Y forces and distances were all in the 2D plane of X and Y. The moment was only about the Z. But now we're getting forces that are in three components, and there's a potential to get a moment, a spin about three axes. The important thing I want you to remember, though, is we are calculating the moment about point C. So we are calculating the moments, we're actually looking at the components of the moments. And I want to keep going before Dave and Jason ask a question. All right. So what did I get? I got a negative. Everybody's with me, right? I got a negative 180 spin in the X. Here's the X. On your piece of paper, you want to draw it. It's a negative. So first, put your thumb in the direction of the X. This would be the correct spin if what? Where am I? I'm up to Edgar.
If it was to be positive.
Correct. If the spin about the x-axis was positive, this spin is correct, but it's negative. So my thumb is pointing in the other direction. And does this, actually, I'll do it in red. Does that look right? This is supposed to be over this. This you could see is under. This is this is a negative moment about point C, X. For a moment, I want you to stop and not think about this being a spin. A moment is a vector. It has an X, Y, and Z component. If this was a force, you'd have no problem. You know, it's being pulled in the negative X direction. It's being pulled in the positive Y direction, and it would have a negative push or pull in the Z direction, right? You're all comfortable with the three-dimensional force. Well, it's still a vector. It's just not a push or a pull, it's a spin. These are the three components of the spin. The Y spin is positive. Here's my Y. Put my thumb in this direction. That's a positive spin in the Y. And the Z was negative. I put my positive in the Z, but it's negative, so it goes this way. The important thing to know, though, is, well, there's many important things, but you have to draw, if you want to draw the spin, you've got to draw a new axis. So if you want, cross out the old axes so you don't get confused. The key is we are finding the moment about point C. And we're finding the X, Y, and Z direction.
Question.
So, okay, question. Matthew.
So the moment vector that we just got, that's like the normal vector, or like
Yes.
that's like the vector, and the plane normal to that is like the plane that it's spinning on.
Excellent. Excellent. Yeah, you're moving us in that direction. So now, because, and we'll say that again. We'll say that in a minute. I'm up to Elizabeth. Elizabeth? Okay, next. Eric. Oh, Elizabeth, you here?
Yeah.
Okay, Elizabeth. I have the X, Y, and Z component of this moment. How could I find the magnitude of this moment? Think of it as a vector, like I just said. It's a vector that has X, Y, and Z components. How do you find a magnitude of a vector? You're muted.
Oh, sorry. What was the question again? Sorry, you keep freezing and my internet's also cutting.
Okay, Elizabeth, you want to make sure you get a free hotspot from Cabrillo. Do you have a free hotspot from them yet?
I don't.
Okay, so you want to get it. It's week 4 of the semester. What you want to do is fill out that form, go to the engineering student Canvas site and fill out a form to get it. Okay.
Okay.
Jason Lee, I think there still are some more. There's another shipment coming in. Okay, so let me go to Eric then. Eric, how do you find the magnitude of a vector?
It's the square root and
Right.
the component squared.
Yep. And it comes out, does anybody have the number?
237.1.
Think. 237.1 Newton meter, and you could still see it. Okay, thinking back to forces, right? This is one way to represent a vector, right? We're up to Gerardo. Gerardo. This is one way to represent a vector, right? And what is it called? Remember we called it vector form?
Sorry,
What's another way to represent a vector? Magnitude and?
Direction.
Direction angles, right? So can we find the direction angles here? It's the inverse cosine of mx over m. Inverse cosine of my over m. And the inverse cosine of mz over m. And let's find those. I don't know if I have them, so you guys have to find them. Yeah, I thought I did the problem, but maybe I didn't. I can't find it. What is it? Negative 180 divided by 237.1 equals inverse cosine. 139.4 degrees. Keep using those to 1 decimal place. 36 divided by 237.1 inverse cosine. 81.3 degrees. And 150 negative divided by 237.1 equals inverse cosine 129.2 degrees.
That's what I get.
Great. Okay, so what checks can I do? There are 2 checks I could do on these direction angles. Where are we? We are up to Hyoji. What checks can we do on direction angles? Hyoji?
Yes.
We did this before. We have direction angles. What check can we do for it? We did it with components.
Actually, I'll pass this time.
Okay, yeah. Isaac?
Cosine squared of each of them, I'll add
Right,
them all together.
cosine squared theta x plus cosine squared theta y plus cosine squared theta z is equal to 1, and it works out. Actually, somebody should check. What's the other check we could do?
Oh no, you didn't do it.
No, I didn't, but I'm going to say it's okay. All right. Jack. Jack, are you here? Yeah. Okay. What's significant about, notice if I had a negative value of my moment, what kind of angle do I get?
Obtuse angles.
Right. And if I have a positive moment?
Acute.
Acute. So I'm going to do the acute obtuse check. Negative x, negative y, sure enough, I got obtuse.
Can you show us what the direction angle of a moment physically represents? I'm not sure I've got my head around it yet.
Yeah. So, okay, is everybody, before we go on, I want to make sure everybody's with me. Everybody with me? Okay, so let's take a look at this. And what we're going to do is think about what Daniel said. What Matthew said. So Matthew said, and we know this already, whenever we do an R cross F, the vector we get is perpendicular to the 2 given vectors. Okay? So we have our force vector here, and we have our R vector here. So think about where is this thing? Here's a safety pin. Can everybody see the safety pin?
Yeah.
This is the head. Where is it coming out here? We know it's perpendicular to this. Here's R, here's F. It's somewhere here coming out. But how do I know where it is? So you guys tell me. What's the value of the, and it could be coming out here, or it could be going out the other way, right? We just know it's perpendicular. It's perpendicular. Here's my plane, right? It's a 3-dimensional plane that's formed by my R and my force. I know it's perpendicular to the plane. It's either coming out here or it's going back. So Jason with an E, How do you know whether, let's try one. How do I know? Is it coming out at me or is it going back?
There we go. Well, let's see. Think that the way that I would explore that, if you could zoom out actually a little bit, that would be great. Yeah, and then scroll up a little bit.
Well, I don't know. I can't get, oh.
Yeah, scroll up. I just want to see the picture. I have the numbers.
Oh, okay.
So which way is it going? If I understand this, you could use the direction angles. Wait, no, that doesn't make sense to me.
Oh,
Let me
yes.
think about it. Yeah, I mean, I wanted to say like, okay, it's at, you put the tail at point, what is that, C, and then you would use the direction angles to hold it off of those X, Y, and Z axes that you have there. That's what the direction angles describe, is the angle between that push pin and the axes.
Excellent. Okay, Jason Lee, could you think of another way we could do it?
Not
So
really.
Jason, the other Jason, used the direction angles to determine how the resultant is oriented. What else do we know about the moment that we could use to orient the direction?
The vectors?
Yes.
You can see the signs on the vectors.
Right. X is negative, Z is negative, and Y is positive. So if I put the pin here, I know it's got to go into the page because it has a negative X.
Right.
And it has a negative Z, so it's got to be down, but it has a positive Y. So I don't know if you could see, maybe a pen would be better. It has a negative X, a negative Z, and a positive Y. So it's coming off this plane in that direction. And this plane doesn't just stop here, right? This plane is the whole thing. That plane that's formed, and it's shooting off the back of the plane. Okay? And that's like, did you guys bring your tops today? Or is it next, it's next week, right?
That is next week.
So in this particular problem, which axis is up? So Jordan, in this problem, which axis is up?
I think it's the z-axis.
Yep, the z-axis is up. So on my tabletop right here, my tabletop, not this top, on my table, this is the XY plane. And this, everybody sees this pointy thing, this thing, the axis of my top. I want my top to stay spinning only in the Z. And I'm doing an okay job, not too good. But if you view it from different angles, you see that it's not really only, let's see it, let me try doing it from the side. You could see that it's not just spinning on the Z, right? When it's spinning like this, there is a component of the spin that's in the Z, but there's also a component in the X and in the Y. So you guys are totally comfortable with understanding if there was a force in the X, a force in the Y, and the force in the Z, the force in the X is pulling point C towards the X. It's pulling point C towards Y. It's pulling point C to Z. You're comfortable with pulls and pushes, with forces. What we're doing now is we're looking at spins. They are vectors too. So even though, or not even though, this force is creating a spin about point C, a little bit in the X, a little bit in the Z, a little bit in the Y, and in the end, we found out that it's oriented in the, see, I'm putting this in the positive X, sorry, the negative X, the negative Z, and the positive Y. So my top is really spinning like this. This force is creating this kind of spin. Okay, questions? Other
After
than
our
Jason,
hat-
wait, I want to give everybody else more chance.
Okay.
So when you get confused about spins in directions, don't think of it about a spin. Don't think of it as a spin. You know vectors. You know force vectors. You know what an x component of a force is. You know what the y component and the z component of a force are. And you know that either somebody's being pushed or pulled. Think of it that way. But then just realize it's not a push or a pull. It's a spin. But it's a vector. You know how to do with vectors. It's just the physical. I'm going to stop this for a minute. It's just the physical sensation is different. The sensation is different. It's not a pull in the x, it's a spin in the x.
So when you were holding up the safety pin,
yes,
it needed to start at C, right? It needed to be touching C and then pointing in that kind of back direction, right?
Yes, and the reason why is because we were calculating the moment about point C. We didn't have to. We could have found the moment about point O or about point D. We could have found this force creates a moment about every point in here. It just depends on what that F stays the same. It's the R vector that's different, right? So if we found the moment about D, the R vector would be here and we would get a different spin here. In fact, if I wanted to find Laura, if I wanted to find the moment about point A, and you actually had this question at the beginning of the week. If I wanted to find the moment about point A due to FAB, what would the moment about A be? Let me show you again. Take a look at this. Here's a force. The force goes from point A to B. And I want to know what the moment is about point A. What's the moment? Does this force create a moment about point A?
No.
No, because it goes right through the point. There's no R vector. There's no lever arm, right? So this force creates different moments about every single point on this picture. The reason I drew my X, Y, and Z axis at point C is because point C was where I was finding my moment about. And I wanted to know what the component, I mean, I could not draw it if I don't want. I could just you could just give me this answer. Give me the moment in vector form, give me the moment magnitude, give me the direction angle, you could be done. But I want you to start understanding physically what's going on, because we are then going to go on to next week, we're going to go on to moment about a point in 3D, and we're going to use right-hand rule totally for it. And we're not going to do it using vectors.
Okay, last question.
Yeah.
So with the safety pin, it'd be touching C, and then we figured out that direction. It was going kind of back and down. Okay.
Right.
The net spin is around that, right? The net spin is around that.
Yes.
We just put. Okay.
Yes.
Good.
Yeah.
Okay.
The net spin is around that. The only problem with it, though, is we calculated 237 by absolute values of these. I have to think more about this.
Okay.
So I don't know. And you know, I don't know the answer to this. I don't know which way it's spinning. Is it spinning this way about the safety pin, or is it spinning? It's got to be spinning. I know the answer. What the hell am I talking about?
Yeah,
I know the answer on my thumb. My thumb is a negative X, a negative Z, and a positive Y. It's spinning like this around my C. So, so if this is the moment of 237, this is the head. This is the head of it. It's going in the negative, it's going in the negative X, the negative Z, and the positive Y. It's spinning this way. It's causing it to spin this way, which actually totally makes sense, because look at this. If I had a rod in here, here's the force. The force is coming down in this direction. It's going to spin this way. Of course I know.
Yeah, that looks
Okay,
good.
thank you.
Okay. I know I still owe you 30 minutes. You will get it. Okay, so I'm gonna go back to the module. And I'm gonna share my screen. And remember, that's a little too small. Okay, so here's the overview of moments. So remember, on Tuesday, we did 2D right-hand rule problems. And the homework is homework 9, and it's already published, and so are the solutions. Here is 2D moment using vectors, 3D moment using vectors, R cross F, and I'm going to publish the solutions. So you could check your work. Okay, so now you have, what's today's date? Oh, the 24th. Oh, you already turned, you were, oh no. Oh, yeah, today is the 24th. You have the 2D right-hand rule due tomorrow. You have the 2D vectors due on the 27th, and they're the same exact problems. So you should get the same answers. And then on the 29th, the 3D moment vectors are due. And then you're going to, the next topic is moment about a line, which we're going to do on Tuesday, which is another vector thing. And then we're going to go to 3D right-hand rule, and the homework will be the same exact thing as the 3D moments. You just have to do it using right-hand rule. Okay. Questions. Boy, I'm going to owe you another 5 minutes. Boy, I'm racking up the time. But maybe you should view it as, oh, I got an extra 35 minutes of teaching from Joanne. But I remember when I was a student, I was always pissed off when teachers went over. So I'm going to give you 35 minutes. We got 1 more minute. I'm going to stop sharing. Any questions?
Joanne, what's the interview about?
Oh, yes. So good. Thank you. On today's class, you noticed if you go back to the syllabus, your grade is a function of homeworks, in-class quizzes, online quizzes, a project we're going to do, and interviews. And I think there's something else, but I can't remember. But there's interviews. So if you click on this interview, open, you're going to interview with me. You're going to have 15 minutes, and we have to schedule a 15-minute block of time where it's just one-on-one, you with me. And what I'm doing is I'm going to show you a statics of particles problem, and I want you to show me how you would set it up, how you would solve for the components and perform the checks, and how you would use the equilibrium equations and solve for the unknowns. Okay? Don't be totally stressed out, but get prepped. Make sure that you're comfortable. It's like an exam. It's like an exam, but I'm not giving exams.
Are we actually writing the thing, or we are just verbally explaining?
You're gonna explain and write unless you can't, we have to figure it out, right? I'm gonna close this for a minute. I'm gonna stop sharing because I want to see you. The best way for me would be you writing it out. So I imagine you're gonna have a piece of paper, and I guess your camera will be on it. Or maybe you'll hook up your phone. I don't know. I would like to see a paper, but if we have to do it verbal, it's fine. It doesn't matter. To me, the important thing is knowing, and maybe it should be verbal. I don't know. I've never done it before. We're going to try it out. And we'll have a series of these during the semester. It's just going to take a long time because I'm meeting 15 minutes with each person. I don't know if you have a suggestion on how to pick times. I'm thinking that maybe I should do a doodle poll to find out from you guys when's your best. I think that's what I'll do. I'll do a doodle poll. I'll do something and find out what times you're available, like Mondays, Tuesdays, Thursdays, you know, and then I'll say, okay, Edgar, you have this time on this week. And Eric, you have this, and Amani, you have this. So I'm gonna find out when you're free, and then I'll give you a 15-minute time. Okay? But it's gonna take a few weeks for us to get through it. Okay. So you have 3 moment homework to do. So class is over. I owe you 35 minutes now. And those of you who want to leave, you could leave. I do have a meeting with Carl at 11:15, so I have about 15 minutes or so, if anybody has any more questions.
Thank you.
Okay, I'm gonna stop the
Julian.
recording. Yeah.
Thank you.
Bye.